All right, so I'm going to introduce some fundamental concepts in GIS and show how that leads into coordinate systems and map projections. So there's really only one law in geography, and essentially it says that everything is related to everything else, but near things are more related than distant things. So things that are closer to each other in space are more likely to be similar than things that are farther away from each other. I think intuitively on some level we all kind of know this, but it's important to see it written down. So for instance, the tree species in Vancouver and the tree species in Burnaby are very similar to one another, right? So Doug fir, western hemlock, red cedar, big leaf maple, alder. It's essentially the same climate, same soil, very little space separates the two. The tree species are all quite similar. Whereas you say go to Miami, Florida, you'd end up with very different tree species, much greater space between the two places, much different climates and soil conditions. So in Miami, you've got lots of palm trees everywhere, whereas here you've got, the temperate rainforest. So things that are closer are more likely to be related. Things that are farther away, less likely. The greater the distance, the greater the dissimilarity. So GIS is all about combining geographic data and doing spatial analysis. We take multiple data layers, which are just abstract representations of reality. We overlay them, see how they interact, to use that to answer questions. One question could be, where's a suitable location for housing development? So you might take some municipal boundaries and overlay that on a roads layer, overlay that on a soil layer, a land use layer, and a topography layer. The housing development has to be in city A or city B. You want it to be within a certain distance of a road. It has to be on a soil type that's suitable. It has to be in a certain land use category, so you don't want it in an industrial area or an old growth forest or something like that. It needs to be on a suitable slope. It can't be on a hill like that. You overlay all those pieces of information, you can answer a question. So we'll get in more detail on how to do actual spatial analysis later, but I just want to introduce the concept. So what types of data do we use in GIS? GIS data typically has both spatial and non-spatial components. So the geospatial data is the coordinates, anything relating to position on or near the Earth's surface. And then all the other data is non-spatial. So that's all the attributes and descriptors that relate to the location. So that's things like population statistics, mean income, rental costs, age, how many people live in an area. It can be things like land use, so property type or zoning, land cover, whether it's forest, agriculture, urban, etc., and physical attributes about a place, so rainfall, temperature, tree age, species presence, things like that. Lots of different types of attributes can be related to a space. And how do we link the spatial and non-spatial data? So there's quite a few different spatial data models that you can use to work in a GIS. We're just going to focus this term on the two most common types, raster and vector data. You get into an intro or an advanced GIS course, maybe you'll learn about some others, but for now we're just going to focus on these two because they're the most common and widespread. So you've got raster and vector data. Raster data has a fairly simple structure. It's just a regular grid of cells, and each cell has a single attribute. You can think of raster data as like a picture or a photograph where you have just pixels, and each pixel represents the value for that space. It's pretty good for continuous fields, things like precipitation and elevation, but it can be used for other things as well. And I'll get more into detail about that next week. I'm just introducing the concept for now. Whereas vector data has a more complex structure. We represent entities in space using points, lines, or polygons. And then we can link many different attributes to any one shape. And they're typically better for discrete objects like buildings, roads, hospitals, things like that. But again, they can be used to represent a wide range of things. And I'll talk more about them. I'll introduce rasters and vector in more detail next week, along with the pros and cons and when you might want to use one versus the other. But how do we go about getting data about the world into a GIS in the first place? We rely on a handful of different techniques. We can use manual surveying, remote sensing, or we can scan and georeference maps that already exist, or we can digitize, create new information by tracing out over a map or a satellite image. So surveying is the oldest form of spatial data collection. I talked about that in the intro lecture on Tuesday. Introduced some of the oldest surveying techniques with the rope stretching and then the line of sight tools like the GORMA. So the modern tool that we use is called a theodolite, and it's essentially just building on those ancient tools. And you've probably seen people, maybe on the side of a road or a construction site, using one of these things. It's called a total station, or commonly sold as a total station. The scientific name for it is a theodolite. And if you've ever been on a hike, maybe you've seen one of these things at the top of a mountain or along a coastline or something. This is a survey marker. And so what you can do is you can measure angles and distances relative to a known point and use that to calculate the position of new points using a process known as triangulation. So here's a little illustration of how you can go about it. You can use the angles and the distances you measure to calculate the exact position of coordinates from a known point. So here's just a quick little illustration of how to do that. So imagine you're lost while you're hiking. You don't know exactly where you are, but you see a sign that says you're 10 miles from a town. With that information, you know that you're somewhere on the circumference of this circle, 10 miles away from point A. You see another sign, or you remember stopping 6 miles ago at a trailhead, and that one was 11 miles from town A. So then you know that you're 6 miles from B and 10 miles from A, so you're at one of the 2 points where those 2 circles intersect. You get a third piece of information. Another sign says you're also 10 miles away from another town, so now you know you're at the intersection of these 3 pieces of information. And so the process of triangulation just relies on the location relative to 3 other pieces of information. So in addition to surveying, we've got remote sensing. This is making an observation from a distance. It can be satellite, aircraft, or land-based. Typically satellite or aircraft when we're talking about remote sensing, but there are some other applications. And it can be either passive, where we're just measuring reflected sunlight, or it can be active, where we're actually sending out a signal and measuring what comes back. So if you go to Google Earth and you turn on the satellite base map, that's passively collected satellite imagery. You have a satellite orbiting the Earth, taking pictures of the light that's reflected off the Earth's surface. And that's most of the remote sensing imagery that we use is passively collected from a satellite. We've also got active remote sensing. So for instance, the shuttle radar topography mission is an example where the space shuttle orbited the Earth, sent out a radar pulse, and measured how long it took for the pulses to come back in different locations, and used that to map the topography of most of the Earth. We've also got LiDAR, or light detection and ranging, instead of radar, which is radio detection and ranging. And so LiDAR can provide higher resolution imagery. They're often smaller. They can either be land-based or aircraft-based. So these pictures are an example. That's me and my master's supervisor back in 2015. We were part of a project in New Zealand where we used a LiDAR to actually measure aerosol dispersion from a helicopter. So this helicopter is spraying tracer dye to represent pesticide. And we use this LiDAR to measure how that plume moves through the air. And similarly, you can use it not just to measure particulates in the atmosphere, but you can use it to measure the land surface or trees or things like that. And so the way it works is there's a laser on top here that shoots out a pulse, and then there's a telescope below that picks up a signal. And so the laser goes out, and some small fraction of that pulse bounces off the particles that you're looking at. It's captured by the telescope, and you can figure out how far away the thing is based on how long it took for that signal to return, and you can figure out how dense it is based on the fraction of the initial pulse sent out that you get back. So the same concept applies to radar images if you're looking at, say, precipitation, for instance. And then another airborne measurement, this one often passive, but again can be active, are drones. So drones are a great tool that have come about more recently for mapping, collecting aerial imagery at very high resolution, fine scale images. And one of the advantages is you can get them at high temporal resolution too. So for instance, I've used drones in my own work in the Arctic to do landscape surveys and vegetation monitoring. So you can fly a drone over a field site at repeated intervals and map the vegetation change and get really high resolution imagery of the land surface. So lots of different types of remotely sensed data. Other ways to get data into a GIS, you can scan and georeference old paper maps. So you're actually going to get a bit of an intro to that in Lab 1. I've got a whole video showing you how to georeference, so I'm not going to belabor this point. And then there's digitizing, where you can either do a manual sketch or trace over a pre-existing image. That would be tracing over a scanned map or aerial photographs or satellite images. So you're also going to get a little bit of practice with digitizing in Lab 1, and then we'll probably do some more complex digitizing later on down the line. But how do we actually represent the three-dimensional Earth in 2 dimensions? Screens and maps are flat, but the Earth is round. So what do we do here? We have to rely on geographic coordinate systems and map projections in order to take the complex reality that is the three-dimensional Earth and simplify it and represent it inside of a GIS. And so, again, this is like the most abstract and difficult to understand concept in GIS, so why don't we just get the hard stuff out of the way first, and then the rest of the semester should be easy.